Oh yeah, no problem. I got like stats for and then I went to Slash and Slash ID. I was gonna say I converted most of puzzles
Okay, so before we start today, does anybody have questions for me? If you haven't seen the announcement yet, assignment 4 is now available. It's due on the last day of classes.
April 7th?
Yeah, April 7th. So today I want to talk about infinite probability spaces, something we've managed to avoid from up until now. In fact, with a few exceptions, we've even avoided infinite sets, mostly because we were interested in combinatorics, which is counting the sizes of sets, which doesn't make a ton of sense in the case of infinite sets. And so to understand these infinite probability spaces, we have to go back to the basic definitions of involved in probability spaces. And one of them is the set S. The thing we've always called S is the set of possible outcomes. And right up until now, the set S for us has always been finite. If we look at the definition, the sample space, it says it's supposed to be a non-empty countable set. So what does that mean? Well, every finite set is countable, but some infinite sets are also countable. Anybody know offhand what the definition of countable is? Yeah. Yeah. So a countable set roughly is a set that has the same size as the set of natural numbers, so the set of positive integers. What does it mean for two sets to have the same size? Well, we saw one technique for actually proving that two sets have the same size, which is the bijection rule. It says if there's a bijection from A onto B, then A and B have the same size. And there was a little condition actually that for finite sets A and B, if there is a bijection from A to B, then the size of A and B is the same. And even for infinite sets, we kind of use the same sort of rule that we'll say two infinite sets have the same size if there's a bijection from one onto the other. And countable sets are just the sets which can be mapped onto the set of natural numbers, the non-negative integers. Okay? So lots of examples of those things, like the set of all integers is also countable, the set of rational numbers, so those are numbers of the form a divided by b, where a and b are integers, those are countable as well. There's lots of examples. And if you want to do probability, actually infinite sets come up fairly quickly. So here's a very simple example that we'll work with quite a bit, actually. Let's say you toss a coin until the first time it comes up heads. So that's your experiment. that there's some that defines your probability, your sample space, and the probability space on top of that. And very quickly you'll realize actually this leads to an infinite sample space. Why? Because for every integer, positive integer n, there is a possibility that I toss the coin n times and I don't have a head yet. So that means that for every integer n, the size of your sample space is bigger than n, which is really what it means to be of infinite size, is that you're larger than any finite number. So in this example, the sample space looks something like this. Maybe you toss the coin the first time and it comes up heads, so you stop. Or maybe the first time it comes up tails and then heads, or maybe 2 tails in a row and then heads on the third one, or maybe 3 tails in a row and then heads on the fourth one, and so on forever. And a more compact way to write this is that this set looks like tails to the n followed by head, and that's true for n integers n bigger than or equal to 0. Right? 0 tails, then a head, 1 tail, then a head, 2 tails, then a head, 3 tails, then a head, and so on. So those are the set of all possible outcomes for running this, this experiment. Okay. All right. So my claim is that this is the set of outcomes. What is the probability of any one of these outcomes? What's the probability of this? So this is, we're willing to toss the coin as many times as it takes to come up heads, and we toss it, and it comes up heads the first time. What's the probability that that happens? Should be 1/2, right? So we toss a coin once with probability 1/2 it comes up heads, with probability 1/2 it comes up tails. What's the probability of this event, or this outcome? 1/4. So with probability 1/2 it comes up tails the first time, and then independently with probability 1/2 it comes up heads the second time, and the probability of this and this, because they're independent, is just the product of those two probabilities. So it's 1/4, 1/2 times 1/2. And then this one, 1/8, 1/16, and so on. And so that says, actually, if we extrapolate here, that says the probability of this outcome, t to the n h, is 1/2 to the n plus 1. Right? N tails in a row, followed by that last head. Okay, now we should check to see if things are actually making sense. So we claim now that this is the probability function that tells us how to map outcomes onto probabilities. What are the rules that a probability function has to satisfy?
Total has to be 1?
Yep. So there's the sort of dumb ones. The probabilities have to be bigger than or equal to 0. We can check that 1/2 to any positive integer is bigger than or equal to 0. That's not a problem. But the main one, the important one, is that the sum over the whole set S of the probabilities should be 1. So some outcome has to happen. So we need to check that. So that rule says that the sum over omega in S of the probability of omega, that should be equal to 1. So for us, probably this is the nice definition to use for S. So we run let's say our counter x starts at 0, and it goes all the way up to infinity, and we look at the probability of t to the x h, which we have written down here. This is the sum, x equals 0 to infinity of 1/2 to the x plus 1, which for us is, this x plus 1 is kind of annoying, so let's get rid of it. Right. 1/2 to the x plus 1 is just 1/2 times 1/2 to the x. And so we have a sum where every term is multiplied by 1/2, so we can just bring that 1/2 outside. Now what? So now we have to remember, we would like to show that this thing is equal to 1, and so that means we need to remember even what this means. What is an infinite sum like this? Anybody remember the definition of something like this?
Are none of the summation rule?
No, just an infinite sum like this, we see them and it runs up to infinity, but we're not really sure what that means. We can get some intuition here just by expanding it. Like, for example, let's do that. Let's just expand this thing. So this last thing is, we've got the leading 1/2. What is 1/2 to the 0?
1.
1. And what's 1/2 to the 1?
Half.
And 1/2 to the 2, quarter, 1/8, 1/16, and so on. So we can kind of gain some intuition about this thing, this infinite sum, or at least we can convince ourselves about what it looks like. And the way I like to think of it is, imagine you have a stick whose length is 2, then this first term here, 1, is half the stick, right? Agreed? That's the first term. What's left when you take away half the stick is a stick of length 1. And the second term is 1/2, is half of that thing. So you take that away, and what you're left with is something of, again, of length 1/2. And now the third term is 1/4, which is half of that thing, leaving us with 1/4. And then the fourth term is 1/8, which is again half of what's left, leaving us with 1/8. And I can do this forever, and I'll never quite get to 2. So this is what's called Zeno's paradox. It's a sort of question posed by this Greek philosopher, I guess, named Zeno, who would argue, he had all kinds of these things, but he would argue that, nobody can ever finish a marathon, because before you can finish a marathon, you first have to finish a half marathon. And before you can, that still leaves you with a half marathon to finish, and before you can finish that, you have to finish a quarter marathon. And before you finish that, you have to finish an 8th marathon, and so on. And so then his conclusion, which was wrong, is then you can never finish a marathon because this goes on forever. So that's nonsense. But because the time it takes you to do each of those things is also getting smaller. But that's the sort of the way to remember this thing. And with that, we could convince ourselves that this all up here adds up to 2, which we're also multiplying by 1/2, so it's 1. that's not totally satisfactory because it requires this kind of heuristic argument, and we'll see a few times in this course that we would like to be able to evaluate these sums for sums that look kind of like this, but it's maybe not 1/2 to the x, but it's 1/3 to the x, or 3/4 to the x, or something. So we want a general rule. So we really need to look at what this definition, what this really means. So when I say the sum x equals 0 to infinity of, no, let me fix this. Let me change x's to i's. Or here we can make x's n's. So we want a sort of general thing, and let's say take this thing from I equals 0 to infinity, and I'm interested in x to the I, so something like that. There's nothing special yet about what's in here, but what does this mean? Let me write down the definition of this thing. This is actually a limit. And it's a limit as something goes to infinity. And what's that something? It's the upper bound of that sum. So what does it mean to say you have a sum which runs from 0 to infinity? Well, actually, that sum, the value of that sum, if it exists, is the limit as n goes to infinity of the sum running from 0 only up to n. So it's the limit of finite sums. And finite sums we know how to deal with. So the way you attack these things is you solve this finite sum, you get a normal looking expression for it, and then you take the limit, that expression will have capital N in it, and then you take the limit as n goes to infinity of that thing. Hopefully you have a rule for that, or it's easy to see what that limit is, and that's the value of the sum. And possibly, actually, the limit is not defined, in which case the value of the sum is not defined. So always hiding within an infinite sum like this is a limit. And if you really want to be certain that you have evaluated an infinite sum correctly, you have to go to this definition with the limit. Because there's a lot of things that you might do with sums, finite sums, that are just not safe to do with these infinite sums. In fact, by playing around with finite sums, in particular splitting infinite sums into two infinite sums, you can prove all kinds of things that are simply not true. All right, so that says if we want to know the value of this infinite sum, we should figure out the value of this finite sum. And so here's a claim. Let me make sure I don't get off by 1. For any x not equal to 1, and any n bigger than or equal to 0, the sum I equals 0 to n of x to the I is equal to 1 minus x to the n plus 1 over 1 minus x.
Is that n plus 1?
This is n plus 1. Yeah. So this is the thing that I would like to be able to evaluate, and the claim is that that's actually equal to this simple closed form expression here. How do you prove that? Let's just rewrite that. That's the same thing as saying that take this thing that we would like to prove, multiply both sides by 1 minus x. So 1 minus x will disappear from the right-hand side. So we'll just have 1 minus x to the n plus 1, but we'll lose it in the denominator. And we get this side, whatever we're going to get is multiplied by 1 minus x. And now we have this sum. What does this sum look like? This sum looks like I see a x to the 0, an x to the 1, an x to the 2, an x to the n minus 1, and last thing I see is an x to the n. Okay? So I would like to show that this thing is equal to that thing. So let's look at this left-hand side here. We'll do the multiplication. So 1 times all of this gives me x to the 0, x to the 1, x to the 2, and so on, x to the n minus 1, x to the n. And then I have minus x times all of this gives me, so minus x times x to the 0 is minus x to the 1. Minus x times x to the 1 is minus x squared. Minus x times x squared is minus x cubed. And so on. And how does this end? Minus x times x to the n minus 1 is minus x to the n. And then finally, minus x times x to the n is minus x to the n plus 1. So this left-hand side here is equal to this thing. And what do you see about this thing? How many terms are actually left here if we cancel everything we can? We've got x to the 0, and those cancel, those cancel, those cancel, everything cancels except for the minus x to the n plus 1. So this is x to the 0 minus x to the n plus 1. But wait a minute, what's x to the 0? 1. So this equals 1 minus x to the n plus 1. And indeed, that's what we needed to show.
Where does it come from? You know, the x1, x2, and, you know, up to xn minus 1.
This is just, if you take this sum and you write out what that sum means, right? It says you sum for I equals 0 to n, x to the I, so that means there'll be an x to the 0, an x to the 1, an x to the 2, and so on. Just write out the sum the long way. Sometimes it's helpful to do that, in particular because it lets you see things like this that are happening, that you can, where you can get these cancellations happening. Okay? Yep.
So that is a multiplication, not a subtraction.
This here, this is a multiplication, right? This is, you take this equation, multiply both sides by 1 minus x. So there's the 1 minus x in front up here, and it's gone from down here. Good. So that's the claim. And now let's see if we can use it. Sum I, let's say, for any x, let's be more careful, minus 1 less than x less than 1, the sum I equals 0 to infinity of x to the I is equal to 1 over 1 minus x. So why is that the case? Well, the sum I equals 0 infinity of x to the I, by definition, it's equal to this thing, right? Which we've decided is equal to the limit as n goes to infinity. We figured that out. It's this thing, 1 minus x to the n plus 1 over 1 minus x. Now, if x is strictly between minus 1 and 1, and n gets really big, what happens to x to the n? Does it get really big? No. If x is between minus 1 and 1, then, well, x to the n is getting smaller as n gets bigger, right?
Yeah.
In fact, easier way to see it is the absolute value of x is definitely getting smaller. You don't worry too much about this range from minus 1 up to 0, but even in this range from 0, as x goes when x is between 0 and 1 strictly, then as long as x is less than 1, x to the n keeps getting smaller and smaller as n gets big. So the limit as n goes to infinity of this thing, well, this thing tends to 0. The limit of this guy is 0. So this is just 1 over 1 minus x. That's good. And these things come up all the time. This is called a geometric series. And it's really helpful to know what the value of one of these things is. And what about this condition here where x has to be between minus 1 and 1? Well, it's kind of necessary, right? Because if x is, for example, bigger than 1, then this isn't going to be defined. I mean, this is true, this is true, this is true, but then look at this limit. This has something up here which is bigger than this x is bigger than 1, then take the limit as n goes to infinity of x to the n plus 1. That goes to infinity. So the limit at this point is undefined. So you don't get to make this step if x is bigger than 1, or if the absolute value of x is bigger than 1. And if the absolute value of x is, even if it's equal to 1, you have problems. Okay. All right. Good. So let's remember that. Save it over here. For minus 1 less than x less than 1, the sum I equals 0 to infinity of x to the I is 1 over 1 minus x. Okay. Now it's time to play some gambling games. Well, I guess we should check this. What happens when x is a half here? So when x is a half, this is 1 over 1 minus a half, which is 1 over 1 half, which is 2. And that agrees with what we decided over here. The sum equals 0 to n equals 0 to infinity of 1 half to the n was 2. And then we multiply it by half to get 1. Okay. So let's play a coin tossing game since we have the whole setup over here. And here's the game. There's 2 players. I'll be player 1, and you can be player 2. And the game that I want to study is called First Head Wins. And you have player 1 and player 2 take turns flipping a coin. And the name says it all. The player who flips the first head wins. So before we think about this game too deeply, which player would you rather be? Yep. Player 1. Why player 1? Okay, so player 1 gets to toss the first coin, and that coin comes up heads with probability 1/2, which means if it comes up heads that time, that means player 1 wins. So that already means player 1's probability of winning is at least 1/2. And even if he doesn't get ahead on that first coin flip, well, the game continues from that point onwards. There's still some chance that player 1 will win, which means his probability of winning is bigger than 1/2. And if you're playing a 2-player game, and one of the players has probability bigger than 1/2 of winning, then that's the player you would like to be. So, that's good. So we've kind of concluded that player 1 is the lucky player in this game. But we'd like to know more than that. We would like to know what's the actual probability that player 1 wins. So let's look at probability, player 1 wins. Or let's be really slow about this and define A to be the event. Player 1 wins. Okay. Now, what does our sample space for this game look like? It's over here. It's a game where a coin is tossed repeatedly. It's changing hands from player 1 to player 2, but that doesn't matter. The game ends as soon as the first heads is tossed. So the sample space looks exactly like this. And actually the probabilities look exactly like this. It doesn't matter who's tossing the coin, player 1 or player 2. So now we just need to figure out what are the events, this event A where player 1 wins, what does that look like? So here are all the events, possible outcomes. Does player 1 win here? First coin is heads. Player 1 is the one who tosses the first coin, so he wins. What about this one? Player 1 or player 2 here? Player 2. Player 1 tosses tails, player 2 tosses heads and wins. So this one is not in there, but this is player 1 tosses tails, player 2 tosses tails, player 1 tosses heads and wins. And then we can check that we have that outcome. Player 1, player 2, player 1, player 2, player 1 wins. And the next one is 6 tails in a row, and so on. So let's write that concisely. If you want to write that concisely, we have some number of tails that happens, followed by a head. And this number of tails, we're going to call it n. And what can you tell me about n if player 1 wins?
From 0 to infinity.
Yeah, but it's not all values of, not all integers n from 0 to infinity. Yep.
All even.
All even n. So this is n bigger than or equal to 0 is even. Right? 0 is even, 2 is even, 4 is even, 6 is even. But one tail, for example, this one is not even, and player 1 doesn't win, player 2 does. 3 is not even, and in this case, player 2 wins again. And so another cleaner way to write this is t to the 2m h such that m is an integer bigger than or equal to 0. Right? Give me any integer m, then 2m is even.
What does M represent? Like
M is the number of pairs of tails in this even number of tails.
what does M represent if it's even?
Well, so here m is 0, here m is 1 because there's 2 tails. Here m is 2, there's 4 tails. So m is the number of tails divided by 2. All right.
It's divided by 2.
Yeah. So, we'd like to know the probability of A. What's the probability that player 1 wins? So, this is what the set A looks like. So this is just going to be the sum, m equals 0 to infinity of the probability of this thing, t to the 2m h. We know all of these probabilities. Sum m equals 0 to infinity. Probability of one of these guys should be, it'll be 1/2, and we have 2m here, so 2m here. This is 1/2 to the 2m plus 1. Yeah. These plus 1s up here are kind of annoying and irrelevant anyway, so let's do what we did before. This really just means 1/2 times this sum, but only up to 2m. So that's 1/2 times the sum, m equals 0 to infinity of 1/2 to the 2m. Now we need to evaluate this thing. Do we know how to evaluate sums like this? So we've got a sum from 0 to infinity. There's some base here, and then it's raised to this exponent. So it looks kind of like this, right? Sum 0 to infinity, there's a base, it's raised to the exponent, but it's not quite, because here we have m running from 0 to infinity, but we're not taking 1/2 to the m, we're taking 1/2 to the 2m. So we have to massage that into something that looks more like what we want. So that's just 1/2 to the 2m. Maybe you do or you don't remember how to work with these kinds of things. But in general, if I have anything, I'll call it y to the a, and I raise that to the power b, that's y to the a times b. So if you remember how to work with exponentiation, that's what this is. You can do that out in a really longhand way. What's y to the a to the b? It's y to the a times y to the a times y to the a times y to the a b times. And now add up all of those exponents. Each one is a, and there's b of them, so you get a times b. And what we have is this, so we want this to work in the opposite direction. So that says that this should be 1/2 squared to the n. And 1/2 squared is just 1/4. So now we use that here. So we have the 1/2. Still, we have m equals 0 to infinity of 1/4 to the m. And now this thing right here looks exactly like this. Right? We have the index variable running from 0 to infinity. We have a base, and it's the sum we want is that base raised to the power of the index variable. Right? M equals 0 to infinity of 1/4 to the m. And the formula tells us that that is, we won't forget our 1/2, 1/1 minus 1/4, which is 1/2, 1/3/4, which is 1/2 times 4/3, which is 2/3. So player one in the game of first head wins has probability 2/3 of winning the game. So you would really much rather be player one. Player one wins twice as often as player two. Questions so far?
Could you explain to me what you did again, like the 1/2, 1/1 minus 1/4? Where did you get those?
So we got all the way to here where we had this infinite sum that is this geometric series that we've studied already. So we have a formula for sums like this, and the formula says that the answer is 1/1 minus x. So x for me here is 1/4. So I get 1/1 minus 1/4. 1 minus 1/4 is 3/4. And 1/3/4 is 4/3. And 4/3 times 1/2 is 2/3.
What did you do with the 2? You took out 2 and almost like this 1/4 now.
Yeah, so that's what we did here. If I have y, anything to the a, all raised to the power b, that's that thing raised to the a times b. What I had over here was 1/2 to the 2 times m, which is 1/2 to the 2 raised to the power m. And 1/2 to the 2 is 1/4. Yep. Because these are the events where player one wins. So that means that the coin was tossed an even number of times, coming up tails every single time. And at the end of that, after an even number of coin tosses, the coin is back in the hands of player one, and then he makes the winning toss, the head. So, right, so here I had this condition, it's t to the n h, where n is even. And another way to write that is that that's t to the 2m, where m is an integer. Then you only get even. After 2m turns, if the game is not over yet, it's back in player one's hand. And that's true even if m equals 0, because in the very first turn, it's in player one's hand. Okay. All right. Everyone understands? It's all crystal clear? If so, let's make it more complicated. I think I have no choice but to erase. But maybe we'll start erasing here. Here's another game. It's called Second Head Wins. Almost the same rules. P1 and P2 take turns tossing a coin. The player who gets the second head wins. So, those are the rules of the game. It's almost the same as before, except the game doesn't end when the first coin toss comes up heads. The game continues after that until the second coin toss comes up heads, and whoever made that coin toss is the winner. Would you rather be player 1 or player 2? So who would rather be player 1? Who would rather be player 2? Okay. And then the most prefer player 2. Actually, most prefer not to play the game, which is if there's money on the line and you're not sure, that's probably the best course of action, because if there's some external force pushing you to play the game and you don't understand it, the odds are, it's not odds, it's not probability, it's quite likely that the game is not working in your favor. And whoever's pushing you to play it knows that. Okay. So, the only way we're going to know this is to work through it. So, we have to start from the beginning because nothing of what we've done so far is really complete enough. So, from the beginning we need to define our space of possible outcomes of this game. And I don't want to start drawing them out long. I don't want to write them out the long way, but let's just think about how the game goes abstractly. The coin gets tossed for a while, coming up heads every time. Or sorry, coming up tails every time. So for a while we toss the coin, and it comes up tails. Maybe n times. And then it comes up heads the first time. And then we toss it some more, and it's always coming up tails. A different number of times, possibly. And then finally, the second heads comes up and the game is over. The person who tossed the coin right here is the winner. So that's for any integers n, m, bigger than or equal to 0. And that captures everything, right? So the game is never over after one round. So even if n and m are 0, that means player 1 tossed head, and then player 2 tossed head. And then the game is over.
What's N and M again?
N is the number of tails before the first head, and M is the number of tails between the first head and the second head.
Oh,
So that's all of the things that can happen. And so let's look at the event. A, player 1 wins. Okay, so for player 1 to win, what do those look like? So there were some tails, a head, some tails, and now the coin is supposed to be in player 1's hand. So that means all of this here, all the stuff that happened up till that point, that should be an even number, right? Because it starts out in player 1's hand. So if you played 2 rounds, then it's back in player 1's hand. If you played 4 rounds, it's back in player 1's hand, and so on. So we can write that thing as t to the n, h, t to the m, h, such that n plus m plus 1, that's how many coin tosses took place here, is even. Okay? So far, so good? Yeah? Okay. Good. All right, this looks complicated. I don't immediately know how to evaluate this sum because it's got these two variables and this weird condition that the sum of those two is even. So I won't be able to do this trick of just multiplying by 2 because multiplying by, I can get the sum of these things to be even or odd by having, for instance, this is odd, this is even, this is odd, or even they're both even, in which case this thing gives me odd. So just this multiplying by 2 trick won't work. So I will use divide and conquer. I have this complicated event, which I would like to break down into simpler disjoint events that I can understand. And so let's see how player 1 can win. So player 1 can win this way. Player 1 tosses the first and second head. In that case, player 1 wins, right? Or player 2 tosses the first head. And player 1 tosses the second one. Right? So that's all the ways player 1 can win. I mean, player 1 only wins if they toss the second head. And somebody tosses the first head, it's either player 1 or player 2. So this is exactly all of the ways that player 1 wins. Yep.
Sorry, why do we n plus m plus 1 is equal?
Because if player 1 is going to win, that means a bunch of stuff happens before the second head is tossed.
But couldn't it be over
Yeah.
n plus 1.
Yeah, and then m plus 1 is even if player 1 wins. Right? So for example, player 1 tosses heads, player 2 tosses tails, and now it's player 1's turn to toss the second head. Or player 1 tosses tails, player 2 tosses heads, and now it's player 1's turn to toss the second head. Yeah. If the sequence is heads, heads, player 1 doesn't win. Player 2 does. What's that?
Are we doing cases?
Yeah. So this event, player 1 wins, you can break it down into two disjoint events. Player 1 wins because, and he tossed the first head, and player 1 wins, but player 2 tossed the first head. That's nothing special there. So we definitely have A is equal to A1 union A2. And A1 and A2 are disjoint because in these sequences, player 1 tossed the first head, and these sequences, player 2 tossed the first head. So that means we can use the sum rule to get probability of A that way. Now let's look at what these things look like. Okay. Player 1 tosses the first and second head. So there's some tails, then there's a head, then there's some tails, and then there's a head. Okay. Player 1 is supposed to, in the event A1, player 1 tosses the first head. So then what's the value of n? Even or odd? Has to be even. So this has n has to be even. Okay. Then player 1 tosses this, so this is n bigger than or equal to 0, and even. All right, so player 1 has just tossed the first head. Now a bunch of these things happen, a bunch of tails show up, and now player 1 is tossing this one. So m of these tails showed up from the time player 1 tossed this head until this second time player 1 tossed this head. Is m even or odd? Odd. So think of it this way. If player 1 tosses heads first go, he gets the first head. And if he wants to win, the coin has to come back to him. So for example, he'll win if player 2 tosses tails, and then he tosses heads. So that would be a 1 tail. Or if there's 3 tails, or if there's 5 tails, or so on. So here we get m bigger than or equal to 0, and this is m odd. So that's what that event looks like. Now, we already saw what to do with these weird things when you have these weird constraints, n is even, and we'll also see m is odd. It's kind of awkward to have that over here. It's easier to just write it in these exponents. So instead of saying n is bigger than or equal to 0 and even, let's just say that this thing should be 2k for some integer k, which is bigger than or equal to 0. And instead of saying that m is bigger than or equal to 0 and it's odd, let's just say that this thing should actually be 2l plus 1. And that's for l bigger than or equal to 0. So all the even integers that are bigger than or equal to 0 are of the form 2k, where k is an integer. All of the odd integers bigger than or equal to 0 are of the form 2l plus 1, where l is an integer. All right. And we can do the same thing for A2. Let's see what that looks like. So in A2, it's the same setup, except now player 2 is supposed to be the one who gets the first head, which means that the number of tails before that first head should be an odd number, right? It could be 1, in which case the coin is in player 2's hand when it tosses the first head, or it could be 3 or 5 or so on. So we'd write that as 2k plus 1. Then we get a head. This is a head that player 2 just tossed. That means right now the coin is in player 1's hand. So we get a even number of tails followed by the head, which is the coin still in player 1's hand. So that's what that looks like, and that's for K and L bigger than or equal to 0. So we just need to calculate these probabilities of A1 and A2, and we're done. Should be easy, right? K is, well, it depends which one you're asking about, but this one, K is the number of tails before the first head divided by 2, and L is the number, is the floor of the number of tails before the first head divided by 2. Well, because I need the number of tails between the first and second head to be odd in this setup, and down here I need it to be even, but then I need the number before the first head to be odd. Okay, so let's just look at probability of A1. That's the sum. K equals 0 to infinity. With the sum, L is equal to 0 to infinity. The probability of this thing for this K and L, let's be super explicit about it. This is T, what did I say? This one should be the even one, then head, then 2L plus 1, then head. So this is just a very specific sequence of coin tosses. It's in one particular sequence. So I get 2k tails, then 1 head, 2l plus 1 tails, then 1 head. So the length of that sequence is 2k plus 2l plus 3. Right? That's 2k plus 2l plus 1 is the number of tails, but then there's also 2 heads in the sequence. So the probability of getting that particular sequence is exactly this. And let's put the sums around it. Sum. Okay, 0 to infinity. L is 0 to infinity. 1/2 to the 2k plus 2l plus 3. All right. Does this look like anything I know how to do yet? Not so much. So let's beat it up the way using some of the tricks we've learned. There's an annoying plus 3 up here. So that means that there's a 1/2 to the power 3 that multiplies everything, every term here. Let's pull that out front. So far, so good. All right. Now, I just focus on the inner bit here. I have an index variable running from 0 to infinity. That I like. It's showing up in an exponent, but there's this other annoying thing that's also in the exponent. But I mean, it really, let's parenthesize this so we really see what's happening here. And this is two nested loops, an inner one running from L over L and an outer one over K, which means that the inner one runs from 0 to infinity without the value of K changing. And then the value of K increases by 1, and then the inner one runs again. And the value of K increases by 1, and the inner one runs again. Which really, we've done this trick already that says that when the value of K is fixed and this inner loop runs, then all that's happening is everything gets multiplied by 1/2 to the 2K. And that's true for everything in this inner loop. And then 2L. And that's safe because this value K doesn't change as we run through this loop. It changes several times, but only after running through this inner loop. All right. Do we know what to do now? This we've seen before, haven't we? What is this? Yeah. So this infinite sum, L equals 0 to infinity of 1/2 to the 2L, is actually 1/4 to the L. It's the sum L equals 0 to infinity of 1/4 to the L. And we can skip ahead because we've already done all of these steps before. Does anybody remember what that evaluates to? 4/3. It was 4/3, but then there was a half lying in front that we multiplied it by. So all of this, we did the work for it. It evaluates to 4/3. So we've still got our 1/2 to the third. We still have our sum K equals 0 to infinity of 1/2 to the 2K. But everything in each one of these things ends up being 4/3. Do we know what to do now?
Where does the 4/3 come from again?
4/3 is the value of this sum. We did it when we were studying the original game. So it came up in the original game. Yeah. No, that's an 8. This is 1/8.
No, the 1 over 2 is okay.
Yes, exactly. Good. So this is the same sum again, right? That thing there, that's the same thing again. So that says that what we get is 1/2 cubed times 4/3 squared. The 3 in the exponent up here, because that's the length of this sequence. 2K plus 2L plus 1 plus 2 heads. Yeah. So the number of tails is 2K plus 2L plus 1, and then there's 2 additional heads. And so the probability that I toss that many coins and they come out exactly that way is exactly 1 over 2 to the number of coin tosses. So that's where this 3 comes from. Okay, so what is this? On the bottom, we have an 8. On the top, we have a 16. And on the bottom, we have a 9, which is 2/9. So, probability of A1 is 2/9. Probability of A is the probability of A1 plus the probability of A2. What do you think is going to happen if we compute the probability of A2?
Probably the same.
Yeah. So it's going to work out the same. It's also going to be 2/9. I think you can almost see it. Right here we have 2k and 2l plus 1. Over here we're going to have 2k plus 1 and 2l. But, I mean, multiplication distributes over addition. So we do this almost the same calculation and get the same answer, 2/9.
Why did you have to square 4 to the 4
4/3 here, because this is 4/3. That's what I figured out here, and then this is also 4/3. So this 2/9, not only is it equal to the probability of A1, it's also equal to the probability of A2, which means that the probability of A is 2/9 plus 2/9 is 4/9. And in this game, so probability of A is the probability that the first player wins this game. It's only 4/9. 4.5/9 would be a half. So this is less than a half. So in second head wins, player 2 actually has the advantage. And that was not, unlike the simple first head wins game, it was clear player 1 had the advantage. In this game, looking at it from the beginning, I could not have guessed who would be better off, whether it's better to be player 1 or player 2. All right. So, questions about that? Yeah. The 4/3 is just the value of this infinite sum. Because we computed it, we did exactly this sum when we were studying the one player, the first head wins game.
But we got 2/3, didn't we?
No, we got 4/3, but it was multiplied by a half. Yep. No, in this case, the player who has the ability to win first? Oh, because
Player 1 can't win on their first live no matter what. Player 2 can.
I would not say that that's a general rule of thumb. I mean, there's really two infinite sums. One of the, I mean, you can also do this for computing probability that player 2 wins, and you just get two infinite sums, and one of them has half of the terms, the other one has the other half of the terms, but it's not clear from the get-go which one is going to be bigger. Okay, so let's try and do the same thing a different way, and using this very simple thing called the law of total probability, which says that if I have two events A and B, then there's a really long-winded way of writing the probability of A, and that's just the probability that B happens times the probability that A happens given B, plus the probability that B doesn't happen times the probability that A happens given that B doesn't happen. So just think of this as either B happens or it doesn't happen. Those happen with probability B and probability not B, respectively. And in one case, then you look at the probability that A happens given that B has happened. In the other case, you look at the probability that A happens given that B doesn't happen. And the proof of this, it's called a law because it's not worth the proof. You just write down the definition of conditional probability here, right? This is probability of A and B divided by probability of B. So the probability of B's cancel out. Same thing happens here with the probability of not B. So now we have probability of A and B plus the probability of A and not B, which is just these two things. A, B, this is probability of A and B, this is the probability of A and not B, and those two things are exactly A. All right, so what does that have to do with what we've been doing so far? Let's summarize things a little bit. So we saw already probability that P1 wins first so remember that was 2/3. Yeah? So we studied this game, first head wins, decided player one really has the advantage there. And now look at this game, second head wins. This game is player one and player two play first head wins for a while until it's over. And then they start playing first head wins again, actually. Once the first round of first head wins is over, that means the first coin came up heads. Now you play first head wins, but the only difference is maybe now player two is the one holding the coin. So let's say B is the event that P1 wins first head wins. And A is the event P1 wins the second part of the game. And by the law of total probability, we have that the probability of A is equal to the probability of B times the probability of A given B plus the probability of not B times the probability of A given not B. Okay. Probability of B, we know. This is P1 wins, first head wins. So that thing we know is 2/3. Probability of not B, this is when player one loses that simple game. So he wins with probability 2/3. So this is probability 1/3. Now, probability of A given B. So that means they've been tossing coins for a while. And player one just won the game. He just made the first coin toss. That's what B means. He won this thing. So he got the first coin toss that came up heads. Now, we're starting the game again, but the first player is player two. Right? toss coins for a while. Player 1 tosses the first head, and now we're back to playing that original game, but the first one playing is player 2. So that's the game where player 1 is at a disadvantage, and he's only going to win that game with probability 1/3, because he's not actually the first player in that second part of the game, actually. He switched places with player 1. So this is only going to be 1/3. And over here, now we're looking at the situation, so probability of A given not B. That means they toss the coins for a while. Player 2 just tossed the first head, and now we start playing for keeps. But that's the original game. Player 2 just tossed the first head. The coin is back in player 1's hand, and we're now playing a game of first head wins. And we know that player 1 wins that game with probability 2/3. So we get 2/9 plus 2/9 is 4/9. Phew, we got the same answer calculating it both ways. All right, so there's a good place to stop today.